The previous lecture concerned war, so it seems only fitting that this lecture should concern taxes. In this lecture, we're going to confront a real-life problem and see what statistical techniques are involved in solving it. And the problem that we're going to think about is producing assessments of the market values of houses in a city. So, for example, if you're the tax assessor, you need to give a value to every house in the city. Well, some houses were sold during the preceding year, and so for those houses, we know the data of interest about those houses. We know their square footage, we know the number of bedrooms, and we also know the sales price. But for the other houses, we know the data about the houses, such as their square footage and lot size, but we do not know the sales price. So our challenge is to give an effective prediction of the sales price of the houses that were not actually sold. In most of our lectures so far, we've dealt with one or sometimes two varying quantities. But in real life, usually there are many more variables involved. And if we think about what makes a house sell for a certain price, there are many features involved, including the square footage of the house, the location, the lot size, the quality of the building materials, many different features. So these real estate features are examples of variables associated with each house in the population. Now, in this case, the population is the population of all the houses in the city or the tax district. The same basic principles that are used when dealing with one variable are used to deal with more than one variable. But everything becomes a little bit more complicated, and so that's what we're going to try to deal with today. As usual, our goals are to organize, describe, and summarize data. In this lecture, we're going to describe methods for modeling data that have multiple variables, and we're going to accomplish this by doing a specific example. So two basic questions of interest arise when there are more variables than one present, and that is, what quantities affect or explain or are related to what other quantities? So, in other words, you know things like the square footage, the lot size, the number of bedrooms, the number of bathrooms, the distance from the city center. You know that all of these things influence the market value of a house. But some of these variables might be related to each other. For example, we would expect that the square footage of the house and the number of bedrooms or the number of bathrooms, all of those will probably increase together on average. So the question is, how can we summarize all these relationships? In particular, sometimes can we eliminate some of the variables as being not important in developing our model, our predictive model for how much to assess a given house at? But can we throw out some of those variables and still get a model that explains most of the price of the house? It captures most of what's going on. Well, okay, so let's begin by taking our list of houses. We're imagining we have houses in the city, and we're going to take the variable that we expect to have the most influence on the value of a house. And we'll start there. Well, so what variable seems likely to have the most influence? It seems like the square footage seems like a likely candidate for the most influential single variable in predicting the price of a house. So to ground our discussion, let's look at a collection of data that consists of having the square footages and the selling prices and other information about a collection of 113 houses that were sold the last year in our example city. What we see here on this list is an excerpt from the total list, but this is a list of houses that were the houses that were sold. You see, we're going to create a model using the houses that were sold and then develop a model that we can then apply to the ones that were not sold. So this is just an excerpt of a few of the 113 houses that were sold. And you can see for each one we have a sales price, we have the number of bedrooms, bathrooms, home square footage, lot acreage, age of the house, and the distance from the city center. So we have all of that information for every single house. We decided to focus on the relationship between square footage as an explanatory variable to the selling price, which is then called the response variable. So we have the explanatory variable, square footage, the response variable, the selling price. Well, naturally, we expect larger houses to sell for more, but we don't expect there to be a perfect correspondence between the selling price and the square footage. So our statistical challenge is to describe how these two varying quantities are related and how closely they're related to one another. Well, the first thing that we want to do is to look at these variables independently. So specifically, let's just draw and look at a histogram of each one. This is a histogram of the square footages of the houses in our 113 houses. And you can see that it has this shape where it's skewed to the right. So this is the histogram of the square footages of the collection of houses. And this is a histogram of the house prices. So we can look independently at the histograms of house prices and the histogram of the square footages and notice that the two histograms are somewhat similar to each other. They're both skewed to the right, as expected from the idea that these two quantities are related to each other, square footage and selling price. We can visualize the relationship between these two variables by making a scatter plot of the two variables. And as you see, the scatter plot is for every house, we put a dot. Namely, we see what its square footage is, and then we put it at that location horizontally, and then we rise up to what its selling price was, and then that's where we locate the dot for that house. In this case, you can see that the scatter plot of these 113 points is a cloud of points that looks roughly linear and goes up to the right as expected, meaning higher square footages correspond to higher selling prices. And we can approximate that scatter plot by a straight line that is the straight line that we actually met before in lecture number 7, which is called the least squares regression line. The least squares regression line is a summary of the data in the same sense that the mean is a summary of just a collection of numbers. It's sort of a central summary around which the data are spread either more or less. Well, just looking at this least squares regression line, we can notice that it fits the data fairly well. And by the way, let me remind you of what the least squares regression line means. It means that for every dot, for every house in our collection, we see what the vertical distance is between the dot and our regression line. We square that difference and add up the squares of those differences. So that sums of squares is a number, and we choose the straight line which minimizes that total sum of square difference. So that's the least squares regression line. Well, so these two quantities, square footage and price, are related, but larger houses seem to have values that are above the line, and meaning that maybe we need to think a little more carefully about those houses separately, but nevertheless, this is still a pretty good fit. Well, after drawing this line, we can compute a number that captures the extent to which the data are spread out from the line. And specifically, after having chosen our least squares regression line, we can actually write a formula for it. And the formula for it is, in this case, exactly this, that the price is equal to $161 times the square footage minus 63,600. Now, there's actually a formula for, there's computer programs that will allow you to just automatically get this formula for the regression line from the data. And if you look at an Excel program or any statistics program, it just will spit out this least squares regression line. So in our example then, we notice that the slope of this line is $161. In other words, the coefficient of the square footage is $161. What that means is that we expect that when we increase the square footage by 1, then this price increases by $161. So you see that it makes sense that in this neighborhood, roughly what this is saying is that as a first approximation, when you add a square foot to your house, you would expect the price to increase by $161. Now, when we look at this total picture of the houses and the scatter plot, we can think of each house as in the following way. We can think of each one as being that the data, the actual value of the selling price of the house, is equal to what its model tells it should be, plus this vertical distance, which is called the residual. So the vertical distance is the amount by which the actual square footage differs from the model that we're creating. So let's give a particular example. If we look at this house whose value is $649,000, if we compute its predicted value given its square footage, you see its square footage is 3,793. It's a big house. That we can put in 3,793 into our predictive formula and do the computation and get that the predicted value is $547,000. Now, in this case, we know that the actual selling price here was $649,000. So the residual is the difference between the actual selling price and the predicted selling price, so it's $102,000. And we can see this visually on our graph that the length of this vertical line corresponds to a difference of $102,000. Our goal, of course, is to try to get a predictive model that predicts the values as closely as possible. So this one was off in this particular case by $102,000. If we look at these histograms of the predicted house prices versus the actual house prices, we can see visually the extent to which they seem to be similar. We're trying to get a predictive model that looks exactly like the actual house prices, and you can see that it looks similar but not quite the same. If we graph a scatter plot of the residuals, that is to say, we say for each residual, remember that's how far off the model was from being correct, we get a scatter plot, and we hope that this scatter plot is a rather random looking collection, because we're hoping that there's no bias to having the residuals in one area being always higher or one area always being lower, and it does look rather random. Our goal is to make the residuals as small as possible. So our concept again is that data equals model plus residuals. When we've made a summary of data, our next step is to ask the question, how well does our summary actually correspond to the data? Whether it's taking just a mean or, in this case, drawing a regression line. So what we're trying to do is to see the extent to which our model explains the actual selling price of the house. So here's what we're going to mean by this very specifically. The original houses had a certain variance to them. Meaning, remember what the variance is. The variance is the square of the standard deviation. The variance is just the average squared distance from the mean to each individual data point. So the variance of the sales prices of these 13 houses is just the mean squared distance from the mean to each value of the house. Okay? So it's a measure of how spread out the sales prices of the original sales prices of houses were from the mean of the sales prices of the houses. The model of the predicted prices gave different values for every one of the houses. You follow me? For every single house, it had a square footage, and that put the predicted value on the line, a slightly different place from its actual value. So we could look at the variance associated with the predicted values of each of those houses. So in this case, the variance of the predicted values is this number, and the variance of the actual prices is this number. The ratio of these two, this to this, is 0.697, which means, and the way this is described is to say that 69.7% of the variation of the house prices is explained by the square footage. You may have heard this term. How much of some varying quantity is explained by some other quantity? How much of intelligence is explained by upbringing? How much of it is explained by genetics? What the actual meaning of that term is that we take a model and we, in this case, a least squares regression line, and we compare the values of the model to the actual values of the selling price, and we compare the variance of the original, how spread out the original selling prices were, we compare it to the variance of the predicted ones, and making that comparison shows us what fraction of the model is explained. Or another way to look at it, an equivalent way to look at it, is that we could look at the variance of the residuals. Remember, the residuals are the differences between what the model predicted prices and the actual prices. We're trying to make them small. What this says is that the variance of the residuals, the leftover parts, is only 30.3% of the variance that you started with. So this model, just using square footage, has explained 69.7% of the variation of the price. Now, by the way, this number, 0.697, is actually the square of the correlation. That was the number, the correlation or correlation coefficient that we discussed back in Lecture 7. It remember, had a formula where but the point is that value of correlation, which was measuring the extent to which our scatter plot was lying close to a straight line, the square of that is actually telling us the proportion of the variation of the price that's explained by the square footage. We now turn our attention to what we would do when we're using more variables than just that one variable in trying to explain the selling price. In other words, conceptually, we know that for all the houses in the city, we know lots of things about them, not just the square footage. We know the age of the house in years, we know the bedrooms, we know the number of bathrooms, we know the distance from the city center, we know the number of garage parking places, the size of the lot on which they sit, the number of floors. We know lots of these things, acreage of the lot. We know all of these things about each house, and so our goal is to get the predicted value. The one response variable is the selling price of the house, and we want to use this other information to help us get a better model, a better explanation for what the actual selling price of the house is. So for each house, we actually have these explanatory variables and one response variable, the selling price, and how can we make use of, how can we deal with this more complicated situation? How can we make use of this other information? Well, the answer is that we do something that's called a multiple linear regression. A linear regression just gave us a single straight line summary of the predictive model based on just one variable, like square footage. Multiple linear regression is a technique that we can use to approximate or summarize the situation where we have several explanatory variables for just one dependent variable. And the idea, though, is to use the same concepts that we've developed for the case of just a single variable, such as square footage and price, and try to follow the pattern of analysis, but apply it to this more complicated situation with many variables. So, first of all, to begin with, we feel that the explanatory variables like square footage, area of lot, distance to the center, that these things actually do have an effect on the house price. That's the first thing. We sense that there is some significance there. But if we were starting from scratch in some other setting, just I'm telling you things about the general strategy of doing multiple regression. If we didn't know whether these variables were having an effect on the actual outcome, then what we would do is something called an analysis of variance, ANOVA. And this basically tests the null hypothesis that none of the variables is a predictor of the response variable. So that's what an ANOVA test says, that at least one of the independent variables is associated with the answer. And we would see that if we have a p-value that's smaller than 0.05, which is typical for taking this null hypothesis threshold of significance, we would say that it's the result of this ANOVA test would say that it would be a rare occurrence by accident to have the data we do if none of these variables were actually explanatory, had something to do with explaining it. So it doesn't necessarily mean, by the way, just getting a small p-value wouldn't mean that the model necessarily explains a lot of the variance that we're talking about, but at least it says that it would explain some. Well, but in our case, this step would just confirm something we already know, that namely that we have some variable that actually does make a significant contribution to predicting the house price, because we already have seen that the square footage is correlated to the house price in a rather significant way. But the idea of multiple regression is that we're going to find coefficients for each of the dependent variables. Just like we found this coefficient, $161 for the square footage, we're going to find coefficients for each of the dependent variables so that when we combine them, they will predict the house price, and hopefully better than would happen with just one variable alone. Right? So that's the goal. So when we run this multiple regression program, what it gives us is it gives us least squares coefficients for the variables. So if we take each house, we could combine the values of the explanatory variables using the coefficients that are produced by the multiple regression, and we get a prediction of the house price. So as before, the residual is just the difference between the actual selling price and the price that's predicted. So let's go and actually see what happens if we run a multiple regression on our collection of houses. Here's what it produces. It produces an equation here. The equation is the model whose answer is the predicted price. By the way, this line and this are exactly the same thing. This is written out in words, and this is just in a more abbreviated form. So these are exactly the same. What it says is that the predicted price for our model is a certain coefficient times the square footage. Now notice that when we use the multiple regression model and we have more variables involved, that the coefficient of the first variable, the square footage, has changed. Previously it was $161, and now it's $190 per square foot. Then we have a coefficient, $49,200, that is the lot size in acres. So this tells us that $49,200, roughly speaking, the way to think about this is that an additional acre will add $49,200 to the predicted value of the house. This coefficient is negative. Negative 12,300 times D. What's D? D is the distance from the city center. So this makes sense. It makes sense because what this says is that, and it's in miles, by the way, so this says that for every mile further away from the city center you go, you subtract $12,300 from the house. You see? So we're interpreting the coefficients of these explanatory variables in terms of a unit change in the explanatory variable has what effect on our predicted value in the model. Now here is an interesting one. negative 24,400 times B, which is the number of bedrooms. Well, this one, when we see this, we have to say, whoa, what is going on here? Why would having an extra bedroom decrease the price of the house by $24,400 per bedroom? When we see a statistical anomaly like this, we see something that sort of hits us and says, well, this doesn't seem right. It gives us pause to try to think about it. Does it make sense or doesn't it make sense? Well, the answer is it does make sense. What this is saying is that if you have a house of the same square footage and you have more bedrooms, then that house is more apt to be a less luxurious house. The quality of the house is less because that means that the rooms are smaller. So adding in the computation, it manifests itself by having a negative coefficient for the number of bedrooms. But that's a rather interesting wrinkle to this thing. We can actually look at our example, looking at the same house. You see, this is the general equation, and if we plug in the values for the exact same house that we looked at before, we see that now the predicted value is $628,000. Its actual price was $649,000, so in this case the residual has been reduced to $21,000. So you see it's a better fit. Once again, we can plot the residuals in this way to see that they're random, and of course we're hoping that they get smaller. In this case, in fact, they do get smaller because we can measure the variance of the residuals and see how small they are, or alternatively, we can measure the variance of the predicted house prices and compare it to the variance of the actual selling prices of the houses in order to see what fraction of the variance in the original sales price of the house has been explained by our model. In this case, and it's traditionally called R squared, it's defined to be 1 minus the variance of the residuals divided by the variance of the actual prices. And in this case, it has explained 77.7% of the variation in price. That is to say, 77.7% of the variation in price is explained by the qualities that we used in our model: square footage, lot size, distance from city center, and bedrooms. And finding the least squares multiple regression model explains 77.7% of the selling price. So this was an example to show how one can use multiple variables to try to explain one variable, multiple explanatory variables to explain one variable. Then what would happen is, once we have a good model, we would apply it to all the houses in the city to give the assessments that would be used for tax purposes. Thank you.